Alright, so in this video I'm going to be explaining another important article on domain adaptation. The title of this paper is Domain Adaptation with Auxiliary Target Domain-Oriented Classifier. So this paper in 2021, which draws inspiration from this paper in 2019 and uses this paper in 2015, which uses backpropagation and draws inspiration also from this article. Domain adaptation aims to transfer knowledge from a label-rich but heterogeneous domain to a label-scarce domain, which alleviates the labeling efforts and attracts considerable attention. Different from previous methods focusing on learning domain-invariant feature representations, some recent methods present generic semi-supervised learning techniques and directly apply them to domain adaptation tasks, even achieving competitive performance. One of the most popular semi-supervised learning is pseudo-labeling that assigns pseudo-labels for each unlabeled data via the classifier trained by labeled data. However, it ignores the distribution shift in domain adaptation problems and is inevitably biased to source data. To address this issue, we propose a new pseudo-labeling framework called Auxiliary Target Domain-Oriented Classifier, and it alleviates the classifier bias by introducing auxiliary classifier for target data only to improve the quality of pseudo-labels. Specifically, we employ the memory mechanism and develop two types of non-parametric classifiers, the nearest centroid classifier and a neighborhood aggregation, without introducing any additional network parameters. Despite its simplicity in a pseudo-classification objective, ATDOC with neighborhood aggregation significantly outperforms domain alignment techniques and prior semi-supervised learning techniques on a large variety of domain adaptation benchmarks and even scarce labeled SSL tasks. So we have a feature extractor G, and we have a classifier. First we do neighborhood retrieval, and then we have our memory bank. Then we have prediction aggregation to get the target-oriented pseudo-labels, also confidence, and then we can use it for confidence-weighted classification loss, because it's not just a simple classifier, it's a confidence-weighted classification loss, and you have standard classification loss as well. So for unsupervised domain adaptation, we are given a label source domain D sub S, and with K categories and an unlabeled dataset T of unlabeled dataset for target, but your target, since it is semi-supervised, we have some labeled data for target as well. Then we have pseudo-labeling, but to fully utilize unlabeled data, this reference represents a simple method with training deep neural network for SSL. It picks up the class with maximum predicted probability as true labels each time the weights are updated. So P sub I is the k-dimensional prediction. The confidence alpha, this confidence alpha before the pseudo labeled term is properly to grow from 0 to 1 gradually, which can mitigate the noises in the pseudo-labels at early iterations to some degree, avoiding the error accumulation. Since the pseudo-labels are not equally confident. In this work, we readily take the maximum predicted probabilities as weights and incorporate them into standard cross-entropy laws, forming the following objective to adapt to model with unlabeled data. Different from this reference where alpha involves two hyperparameters, we adopt a linear scheduler for that. And here we have auxiliary target domain classifier. So they propose a new regularization approach, call it ATDOC, that fully exploits the structure of unlabeled data to get reliable pseudo-labels with the presence of domain shift. So it aims to learn an extra specific classifier for a target domain. However, it is quite challenging to learn F sub t without a labeled target data. Fortunately, there exist some source-like samples whose output predictions are reliable, which can be used to help build the classifier proposed here and teach the remaining samples sequentially. To avoid the trivial sample selection and alternate training, ATDOC employs a memory schedule that collects or stores information of all target samples to generate more accurate pseudo-labels. So we developed two types of non-parametric target-oriented classifiers and describe the details of them. The first one is nearest centroid classifier. So it is one of the most simple yet powerful classifier that merely requires the class centroids. Motivated by prior works which utilize class centroids to bridge the domain gap or domain adaptation problems, we describe the data structure of the target domain with its class centroids. Specifically, we introduce a memory bank to store the information of target-oriented class centroids and dynamically generate pseudo-labels which as nearest classifier for unlabeled data in each mini-batch. So here we have memory bank update. Since the target data is unlabeled during training, we first obtain the one-hot pseudo-labels, then utilize them to update the centroids in the memory bank via exponential moving average. And for pseudo-labeling with the class centroid, we readily construct that NC classifier and generate the pseudo-labels. D here is just the distance between these features and these centroids. Here we adopt the cosine distance as a default. Finally, you use cross entropy. But there is another approach, neighborhood aggregation, because class centroids can only coarsely characterize the domain structure, which fails to depict the local data structure. Therefore, we follow the idea of message passing via neighbors. But to avoid ambiguity in the target predictions, we directly sharpen the output predictions via prediction sharpening and class balancing. Note that sharpening operation, this t, which is equal to one half, would increase the confidence of each pseudo prediction. Besides, normalizing the sharpened prediction with the overall class-wise vector results in the balancing among different classes over the unlabeled target domain. We do not adopt any moving average strategies to update the values in the memory. The memory module keeps updating every mini-batch, and training a parametric classifier involving extra parameters would be time-consuming. So to address this, we present a non-parametric neighborhood aggregation strategy as F. We first retrieve this M nearest neighbors from the memory module, for each sample in the current mini batch based on the cosine similarity between their features and all features in the memory bank. Then we aggregate corresponding soft predictions of these nearest neighbors by taking the average, where n sub I is just the index set of neighbors in the memory module for the data point x sub I. So we obtain a probability prediction. We are learning on the entire target date. And our strategy indeed considers the global structure beyond regularization within a mini batch. And now we can do pseudo labeling. For each unlabeled data, we get the pseudo labels choosing the category index with the maximum probability. Finally, a confidence-weighted cross-entropy loss is imposed. So we employ the standard cross-entropy loss with label smoothing regularization, and integrating these losses, we can have this total loss. Actually, we can readily incorporate L sub NC or LNA to other domain adaptation as an additional loss. Besides, for SSL methods like mix match, we just replace P with one-hot encoding. And you go from any source to any target, and you have different accuracy. So for different methods, you can see different accuracies. For example, the worst case is 58 here, and the worst case here is 60, and here the worst case is from this domain, this source to this target, and also other methods that you can see. And they did an ablation study, but we always do visualization, this algorithm, TSNE algorithm for visualization.